Welcome, everyone. We'll go ahead and get started. Thank you so much for joining us today. This is the Fort Wayne Metals webinar. It's the next in our series of already existing webinars. You guys may have had an opportunity to see previous ones that focused on capabilities and some of our core business segments and products. Today, we're going to take a little different approach, and we're going to look at advanced materials for interventional devices. So we're hoping today to talk to some of our technical experts and find out a little bit more about a series of topics related to interventional devices and materials and mechanical properties. So just a couple little housekeeping notes. If you've joined, thank you for doing so. There is a Q&A section that you can see from the webinar. When you navigate there and ask a question, those questions are anonymous, so those only go to our presenters. So by all means, if you have questions, please put those in the Q&A option, and we'll take a look at those throughout the webinar. Also, if there's any that are directly related to a project that you're working on, we'll not share those in the meeting, but we can reach out to you later to share those. So let's get started. Today, I'm joined by three of our technical experts: Garrett McCord, Senior Engineer; Larry Kay, Project Specialist Emeritus; and Mark Liu, Product Development Engineer. So like I mentioned earlier, we're going to cover a series of topics, and it's meant to just be a Q&A between myself and our technical experts. We're going to talk a little bit about mechanical properties. We'll talk about material selection, and then we'll finish by talking a little bit more about our HHS tube product and its impact on potential uses in interventional devices. So let's get started. Garrett, you're up first. We're going to talk a little bit about mechanical properties. I want to start with the basics. What mechanical properties are most critical in interventional devices such as catheters or guide wires?
Yeah, so the most typical mechanical properties of importance for these types of applications are generally tensile strength, elongation, modulus of elasticity, which is also something to do with material choice, and also sometimes yield strength. And that's mainly if you want to specify the yield strength over the tensile strength, if you know your max load and you want to ensure that your device is not yielding at any point based on those max loads.
Great. So we have an understanding of high-level mechanical properties, but let's dive a little bit deeper. You mentioned tensile strength. How does tensile strength and ductility affect product performance?
So going over tensile strength and yield strength first, this really just drives the main expectation as far as the overall strength goes for both the wire and for the device being designed as well. The higher the tensile strength given a certain size, the more load the wire can handle before failure. And the same goes for yield strength. That just tells you the higher the yield strength, the more load the wire can handle before you start yielding your device or the wire. Also, a higher tensile strength given a certain size for the same alloy will also typically give the wire a stiffer feel. This just means that it feels harder to bend and permanently deform the wire compared to something like an annealed wire, which takes very, very little force to yield. And then next, going over ductility, elongation is actually the specific measure for ductility given in a percentage. This is just the measure that tells us how far a material can stretch before it breaks. So high tensile strength material generally has low ductility, and annealed material or low strength material has high ductility. Both of these conditions have trade-offs that directly influence both the wire and the device as well. And then finally, modulus of elasticity, which I kind of mentioned before, was due to material choice. This specifically defines how stiff the material will feel. And then this measure is just the slope of the elastic portion of the stress-strain curve. So all of these properties, they have a direct influence on the device performance in conjunction with your device design in these interventional applications. Specific to guide wires, pushability, torqueability, and ability to traverse tortuous paths are likely going to be very, very important aspects for that. A simple stainless steel guide wire may be good enough. However, superelastic nitinol is likely worth a look with its special properties. And then to recap, this applies to both guide wires and catheters in these types of applications. A higher tensile and a higher modulus is going to give you a stiffer feel. This generally translates directly to pushability, torqueability, and overall strength and tension and compression, but the trade-off is that the ductility will be lower. And then on the other hand, more ductile material or lower tensile material will give you a softer feel. This might be easier to bend around tortuous paths, but you have to take a look at your overall device design. You have to make sure your pushability and your torqueability, and then also your resistance to crushing or bursting is still acceptable for your application.
Great. Thanks, Garrett. You also mentioned a couple slides ago high strength material. Can you talk a little bit about the challenges? I know you talked about tensile versus ductility. Are there particular challenges when working with interventional applications for high strength materials?
Yeah, absolutely. Most of these challenges really come from development or otherwise process related issues from our end when we're attempting to push the envelope. For example, we just developed not too long ago an ultra strength 304V, which pushes about 480 KSI on tensile strength. Really, whenever we're developing these products, we really have to make sure we dial in that process and ensure that the cost from our end is good so we can stay competitive, which also makes the device competitive as well for the market.
Thank you, Garrett. And as a reminder, if you have any questions for Garrett regarding mechanical properties, you can go ahead and pop those in the Q&A portion. So we're going to move on to Larry and talk a little bit about material selection. Larry, what are the key factors? Again, we're kind of start with the basics. What are the key factors when considering choosing materials for interventional applications?
Tim, there's really four factors that impact your decision. They are the physical properties of the material that you're working with or considering, the mechanical properties, Garrett touched on those a bit, and the chemical properties that result from the elemental construction of the alloy. Cost has to be considered, and while it's seldom the primary factor, you have to consider that as you navigate through the property options that are resulting from the choices that you make. We can delve into these a little bit in more detail on the physical properties side. These properties result from the chemistry specification of the alloy itself. They don't change, or at least change very little upon processing from the ingot to the bar or wire shapes. They are measurements that are not related to the applied forces. So these result from just the elemental composition. The first one is density, which has a direct relationship on radiopacity. Higher density materials are more radiopaque and more visible under fluoroscope. Electrical conductivity and thermal conductivity, again, relate directly from the elements, and the magnetic properties are primarily influenced by iron-based alloys. And if the application requires use in an MRI field, then the non-magnetic alloys are called for. Regarding the mechanical properties, Garrett touched highly on these and spoke about the strength. I just wanted to touch on the fact that these mechanical properties are evaluated by subjecting the material to a load and measuring its performance under the loaded condition. This can be done with both static and dynamic loads, and these properties vary by the shape and size of the material and the processing conditions, as Garrett mentioned. They have some influence by the metal's composition and internal structure. Elasticity is one I want to touch on here, the ability of a metal to return to its original shape after a deforming force is removed, and certainly nitinol materials are the standard when shape recovery is important. And then briefly, the chemical properties. The resistance to corrosion and oxidation is controlled by the inclusion of materials that are fairly stable and do not lose or gain elemental oxygen easily. Metal combinations that create strong metallic bonds help to resist chemical attack.
So there really is a balance. I think this kind of bridges us nicely between what Garrett talked about with mechanical properties and really also knowing that the material selection is important and some of those properties are adherent or compliant to what material you select. As you look at those things, Larry, what are the trade-offs that you mentioned cost? What are the trade-offs between cost and mechanical performance when you're looking at material selection?
Kim, the material performance is driven by the requirements. And so as you add more requirements to the design of the device itself, those increase the mechanical performance needs, and you can expect the cost of the product to increase. Costs are influenced by the raw material cost and the cost to process the material, both primary and secondary cost. And secondary processing costs can include any required coatings or surface treatments that have to be applied. There's a couple different ways to think about these properties and how they relate to the alloy selection. And balancing these requirements is best done with a material selection table or requirements table in a bubble chart format, at least as a guide. Some of the material manufacturers provide material selection guides, and these can be used to assist with understanding the placement of a specific alloy into a selection guide. After reviewing your requirements, decide which two properties that you'd like to compare. You can fill in the data with information from the supplier or generate your own data and make your own chart. Bubble charts have a limitation that they can only contrast two properties, and thus a comparison table like this can help when comparing multiple properties. And the nice advantage of this table is it can also be done with relative properties rather than numerical data. Often you'll need to select a material based on one or two primary properties, and you can accept or apply design controls that tolerate other properties that are not ideal.
Larry, there are so many options out there, both for material selection and mechanical properties. We often have conversations just like this about making selections about what's appropriate for our customers' needs. Let's talk a little bit about materials, but also emerging technologies. So, are there emerging materials or technologies that you're particularly excited about right now?
Yeah, indeed, Kim. There's several that are being developed, and one of the newer exciting technologies is the ability to provide grooved wire shapes in most materials. For example, a grooved wire can be used to add electrical wires down the guide wire or a device that's connect a sensor at the end of a guide wire for any variety of sending a signal or receiving a signal back. Another technology that's occurring is Garrett touched on that some of our high strength materials, both in some standard 304 stainless steels, where Garrett mentioned that we're able to achieve greater than 3.5 gigapascals in small diameter wires. We're also capable of achieving greater than 5.5 gigapascals with tungsten and molybdenum based high density materials, providing strengths that have just not been available to the designer before. On the material side, there's a couple of new developments in shape memory alloys. A nickel titanium niobium alloy has been developed, which demonstrates improved strength to address this issue over traditional nitinol alloy performance. Retains shape memory recovery, but increases the stiffness of the material itself. Another development is a new nickel-free alloy. This is a beta titanium alloy that was developed specifically as a nickel-free alternative for nitinol alloys in medical applications.
Great. Thanks, Larry. I really appreciate you sharing those things. It's interesting. You and Garrett both mentioned stainless steel, nitinol, and alternative options. We continue to see customers asking for smaller and smaller materials with higher strength and better fatigue resistance. So it's good to see things are being developed. If it's something that you're interested in, please reach out and we can talk a little bit more about that. Again, if you have any questions for Larry, please make sure to put those in the chat. So we're going to change gears a little bit and talk with Mark is going to join us here. And we're going to talk a little bit about a Fort Wayne Metals product called HHS Tube and its applicability to interventional devices. Mark, can you start by talking to us a little bit about what makes HHS Tube unique?
So what's going to make HHS Tube so unique is its ability to be customized to meet a wide variety of customer applications. And the reason it's able to be so customized is due to its ability to target multiple different functional and mechanical properties. And these properties include things such as flexibility, torque transmission or rotational control, elongation resistance, and also compression. So this ability to be customized to specific applications and target those mechanical properties comes from both the available product forms and also the design parameters within those product forms. So HHS in its most basic forms is available as a single, dual, or triple layer round wire construction, but it's also available as a dual or triple layer flat wire construction. Then within these basic product forms, there are multiple adjustable design parameters. These include things such as the alloy or material selection, the wire count, the wire size, and also the lay direction per layer. And these adjustable design parameters are just things that can be adjusted that further tailor the HHS to the application's needs. Additionally, HHS allows for multiple different secondary operations to be performed to it. And these secondary operations include things such as swaging, coating, shape setting, multiple different types of cutting that can be applied to the ends, welding, and then also even assembly work can be done with HHS. And these secondary operations can be needed to further dial in those mechanical properties that are desired, or also just as a more convenient way to provide the customer with a more complete end product so that there's less work that they have to do on their end.
Mark, you've given us a good overview of HHS and all the variety of custom options that can be tailored on the product. Can you talk a little bit about torque transmission and flexibility, which might be important in the interventional device space?
Yes, so HHS can be a good option for those applications that require both the torque transmission while at the same time needing to be flexible enough to navigate those tortuous environments. It's the flexibility of the HHS that will allow you to get to that site of intervention. And then once it arrives there, it could deliver that needed rotational control or torque transmission to perform the application. Whether the focus is more on direct torque transmission or more on flexibility or a balance of those two properties, it's the various product forms and those design parameters are what drive that ability to be customized to the application. And ultimately, it's going to depend on the requirements of the application, but HHS tube will take various forms depending on what those needs are. For example, flat wire HHS will likely be more applicable to those applications that require good direct torque transmission, and the design parameters create a thin wall HHS construction, whereas triple layer round wire HHS constructions are going to be more suitable for those applications that require good flexibility while also good bidirectional rotational control.
So, Mark, you spent a lot of time talking about kind of the structure of the HHS. Can you talk a little bit about the significance of the open working channel?
Having that open working channel throughout the length of the HHS is going to simply allow for the needed components to get to that site of intervention. The flexibility of the HHS will allow for the creation of a safe pathway through that vascular curvature. It's going to depend on the requirements of the application, such as the mechanical properties that are desired, and also the design window that is being worked with. But generally, HHS can be produced with an inner diameter anywhere from 3 thousandths to 87 thousandths. Being able to produce to such this wide range of inner diameters is another reason why HHS can be used for multiple different applications.
Great. Thank you very much. As a reminder to people, we do have a Q&A function that does go to the presenters. So if you have questions, I would encourage you to put those in. I do have a couple questions as we wrap things up here. One of those questions is for Larry. Larry, we had a question that I think is an interesting one, and it relates to the grooved wire. One of the questions we had was, you mentioned potentially something carrying current, potentially something with a conductor or a insulation wire. Any challenges that you're aware of, or have you heard of, with putting something like that in the groove and that insulation? Is that a rough edge there, or what's been the experience if you have any?
No, it's a fairly smooth edge, and has a small radius at the end, so it's not sharp by any means. And we can apply this to wire diameters, everything from 0.25 millimeters to 0.50 millimeters. And the groove size itself can be as anywhere from about 15% of the diameter as a usable size up to as much as almost 50% of the diameter. So the wire that can be inserted in the groove can be fairly large, just a function of how much current and needs to be carried on that signal wire.
Perfect. Thank you. Hopefully, that's a question other people had as well. Mark, one of the things that you mentioned in your presentation was around, and I'm going to back up to your slide to ask a quick question for maybe people that aren't as familiar. You mentioned on this slide lay direction. Can you explain what you mean when you say lay?
Yeah, so lay is going to be the orientation in which the wires are laid down into the construction. So if we talk proximal to distal direction, the primary direction of rotation is going to be clockwise. And in that case, your lay direction for your HHS is going to be left-hand lay. But if you were to switch that around and be rotating in the counterclockwise direction, your lay direction is going to be right-hand lay. And typically with HHS, we finish with the primary lay direction on the outer layer, and then we alternate lay direction for each layer.
Perfect. Thank you. Very helpful. I'm not seeing any additional questions in the Q&A chat. I do want to just encourage you, if you have additional questions as we wrap up, please feel free to put those into the chat. It actually looks like we've just had a couple of come in. So another question around groove wire. So Larry, you're back. You're back up to answer a question. For the groove wire, does the groove need to spiral? So or can that groove be straight? So in the picture that we saw, the groove there shows kind of a spiral rotation. Can you speak to that?
Certainly, Kim. Sorry. Yes, it does need to spiral. Most of the applications have a straightening process applied to the wire. And as we apply that straightening process, it does create a spiral pattern in the groove itself. That's correct.
Perfect, thanks. And Larry, I think in that product we're able to supply that in it's traditionally supplied spooled. Is that correct?
I think we would prefer to apply that in straight lengths.
Okay,
Yeah.
good. For
Yeah.
the groove wire, the preference is those are straight lengths, which would be cut. And I think to further what you said, that spiral will that groove will move around
Yes.
the wire in a spiral fashion. Great, thank you very much. There's a question around HHS. Is HHS intended to replace braid and coils for reinforcement layers of a catheter? If so, can you still bond polymer over the outer surface and put a liner in the lumen with lamination? I will point out too, as we've talked about a lot of custom products today, as you further kind of your design and review, there are things that work well. And I think that trade-off of, is this a good replacement for other things that I might be using in my design, is probably a more detailed question we would want to review over. But I know the polymer question is one we get quite often in the liner within the lumen. Mark, can you speak to those?
Yeah, so to answer the first part of the question first, I would say it can be. So some people may be using a braid or a coil, and they can use HHS and find out that it works better based off their needs. It can also be used in conjunction with both a braid and a coil. So you could put a coil on the outside or the inside along with the HHS, or a braid over the outer diameter of the HHS. Regarding the polymers over the outer surface, yes, that is something that can be done with HHS. And depending on what the polymer is, that could be something that Foreign Metals could do. And for a liner on the lumen, that can be done, but that is not something that Foreign Metals is capable of doing.
Thank you for sharing that. Another question related to groove wire again. Larry, you mentioned the type of groove and the shape and the percent of cross-sectional area. Can the wire have more than one groove?
Yeah, we're actually, Kim, we've been able to do as many as 3 or 4 grooves around the wire, again, to allow multiple wire locations inserted into those grooves if that's something that's needed. Yeah.
Perfect, thanks. There is a general question about our capability in terms of coatings. So we do have a variety of capabilities when it comes to coating wire. Obviously, depending on exactly what you're looking for, we have a series of fluoropolymer coatings, as well as the capability to offer polyamide, as well as PTFE coatings. So I would encourage you, if you have a particular application, that we talk probably a little further about that. There's definitely, one of the questions was it around adhesion and how durable the coatings are. So that's very dependent on the coating selection that you make. Some are used more for electrical insulation, as others are used more for lubricity or even kind of adhesion protection of the material that's underneath. Check and see if we have any additional questions.
Yeah, Kim, I see one there asking about common shapes that can be set on the small wire diameters without having to design a mold.
Oh yeah, good. Thank you.
I can address that one for you. We're able to make a variety of shapes in continuous lengths, and those shapes can be triangles, rectangles, half rounds. We make a variety of those and can then apply that shape pattern to wires and supply those shapes on a spool as well.
Thank you. Larry, while you're still on camera, actively involved in ASTM, and we have a question around, does ASTM currently have a standard for 304V? If
Yeah.
not, who? I think you know the answer to this.
Yeah. So the ASTM organization has standards for 304. The V stands for a vacuum remelting operation. And while that ASTM standard applies to the chemistry, it does not currently specify melt methods or modalities. And so our 304V conforms to the existing ASTM standards, but actually there is not a standard for 304V.
Okay, good to know. Thank you. Let's see, another question. I'll try to tackle this one about boutique melting. So we talked a lot about material selection. Many of you may know, or you may have had an opportunity to attend one of our other webinars about our melting capability. We do have a variety of melting capabilities. We made some heavy investments in the last 10 to 12 years to melt, for instance, our own nickel titanium product and have a variety of melting capabilities. But we do have the ability to do, the question was directly related to boutique melting. So we do have the ability within a small melting to look at new materials. So not only to evaluate materials that Fort Wayne Metals will commercialize and melt on small scale, but also the ability to do that for our customers. Those inquiries typically come in through our research and development group. So if you have needs or further questions about what we might be capable of, there's a big variety. So we can take that offline. And this is probably a good time for me to say too, a couple things. This is being recorded. So if you would like to see the recording later, or maybe you missed part of the webinar, please reach out to your Fort Wayne Metals contact. If you don't know who that is, you can get that from our website. There's also a great deal of knowledge on our website in general in terms of what materials that we offer, what materials we work with, more details about mechanical properties and those types of things. I'm going to ask that all of our technical experts come back on camera. Great. I want to thank you guys today for the discussion that we had. I know at a high level, we hit probably the foundational elements to what our customers need to consider when they're creating devices. So Larry, you covered material selection and how to go about balancing what your needs are. Garrett, thanks for covering the mechanical properties and the ability to modify those things and drive that custom product that has an impact on the devices. And Mark, thanks for covering a highlight of the HHS2 product. For those of you that are still on the call, if you have a opportunity and want to watch this video again, it is being recorded, so you can reach out to your customer service representative or your Fort Wayne Metals sales representative and get a copy of that. If there are Q&A that come in later, we will continue to reach out to those individuals and talk through those. We do have more webinar series coming after the first of the year, also to include our research and development group. So thank you guys for joining today. Thank you everybody for your time, and have a great rest of the day.